Yes, we can start, and it is my big pleasure to introduce our speaker today. It is Professor Xia Chen from University of Tennessee, and our audience maybe is familiar with his books. So it is a great pleasure to see you here and to hear your talk. I hope that next semester Xia will visit us. But now we just will have some introduction to the subject. Please.
Okay. First of all, I want to thank the organizers and particularly Andrew for invitation. I have to confess, this is the first time for me to give a seminar talk in this way, and I hope I will survive from this talk. Okay. So here is a topic. That's the large scale asymptotics for the Parabolic Anderson models. Okay, so the Parabolic Anderson model is this definition of that, where that V will be a suitable random field. In this talk, it will be a suitable Gaussian field. So there's a long history of the Parabolic Anderson model investigations. The first, I think I heard about stories that's motivated by impurity of the diamond. But there is another story I wanted to tell. Since today there are some students, is taking part of this seminar, so I want to give this kind of elementary story. So think about that's you have a population models. That means the particles or individuals is spread in the space and move around, also reproduce the populations and die. So the two actions govern this mechanism of the models. One is the birth and the death of the particles with the rate that's giving us a V in, okay. Another is the particles move around. Okay, the rule they move is for each individual particles and given time and space, they are going to move towards the directions which lead to fastest decreasing of the population. This is a typical animal movement because this movement gives them better chance to find enough resource to live on. Since this is not should not be the model for the human populations, because now we know that the human population tend to move to the big city. So this is quite different. So those are two things, rules we give, and we are going to show that this story fit into the Parabolic Anderson equation. Okay, here it is. And look at that's the equation we gave. So this is first equation. The left side basically is the change of the local population. Like we mentioned, this change of local population is by two things. One is the people who move in and move out. That is represented by this sphere integral. Okay. The second term, of course, this 1/2. There's no good reason why you put 1/2. That's just make that the model mathematically looks better later. So second term is the impact on the birth and death. That is the change of the population because of somebody was born and somebody was died. Then you can write this first integral, sphere integral, by that divergence theorem into a multi-integration. Okay, so if you do this, then you are going to rewrite that equation this way. And if we assume that everything is regular enough, then if this thing is true for any domain bounded domain D, then that will lead to parabolic Anderson equations. So that's the story. I always tell my students how you motivate the study of this parabolic Anderson. Another link to the parabolic Anderson model is to the KBZ equations. This is a KBZ equation. And that was by those physicists who are interested about the study of the interface. So formally, the link between the parabolic Anderson equation and the KBZ is by this transformation. Okay, so that's the link. Also, later on, that parabolic Anderson model become a receive new attention from others is because this link recent years. Okay, so the behavior we're going to discuss in the parabolic Anderson, for the parabolic Anderson equation is what I call large scale asymptotics, which means that you consider that the limiting behavior, some parameters go to infinity. Here, particularly, I list two different patterns. One is annealed loss. That means you talk about the moment behavior of the solution when n tends to infinity or t tends to infinity. Another is what we call quenched loss. That means view this as a stochastic process and ask a question about the limiting behavior of this process when x goes to infinity or t goes to infinity. Okay, there are some early results, so I list some names here for that, for the early reference. Now the question is, there is next thing I'm going to talk about is intermittency. So the large scale asymptoticals, actually, we are going to talk about a link to what we call intermittency. So the name of intermittency can be interpreted mathematically and intuitively. So first of all, I want to give the intuitive meaning of intermittency. So think about that the solution U be treated as a function of x. So that means you either fix t or you let t tends to infinity. So that's the only independent variable is x. Then you consider the graph of such functions. That graph must be the graph for a surface. Okay. So intermittency basically show you that's a kind of a image of the graph where that's most of the surface stay in the low ground. That means it's close to the ground. Only with all the Saturn with a very high peak, very much like okay. So in North America, when you take the flight and when you try to arrive some cities, before you land, you are going to see this kind of image. Because most of the people live in those, no height, very low buildings, even that's live in those house. But in the downtown areas, there's some very high-rise buildings. That's the image of intermittency. So that means the surface, most of it stay low, and all the time, certain you see some, occasionally see some high peak. Okay. The mathematical definition of intermittency is by this formulas. And so basically you have to understand, in order to understand the intermittency, you have to understand this kind of, try to solve this type of problem. Now, the next page, I'm going to try to show you why this kind of definition linked to the intuition of intermittency I explained before. Okay, so by the definition and by that kind of what we call Gardner-Innes theorem, this kind of standard transformation in the theory of large deviations. If you, that basically says, if you know anything about the exponential moment asymptotics, then you have to, then you get some kind of a large deviation representation. Here is what we get from that definition. So you get this kind of result. So the definition of intermittency, let me just go back. It basically required that's a superlinear increasing rate for this function of kappa. Now, because of that, that will guarantee this supreme is finite. Okay? This supreme is finite, but on the other hand, this supreme is increasing to infinity with the lambda goes to infinity. So this result basically tells you the height of u or the log of u. The reason we consider log of u most of the times is because in this model, that's u increase exponentially. So in order to consider the magnitude of the solution, we usually take the logarithm. So this basically tells you in the given site, the probability that you got a high-rise building at this given site is exponentially small. And that smallness also is very much depends on the value of the lambda. The bigger the lambda is, the more exponential small this probability is.
Okay. Is parameter x fixed or not?
Sorry?
Parameter x, log of utx, is
parameter x is a fixed. Actually, so we will, that's a good question. So actually, because this parameter x can be given in terms of initial conditions. So we know for this kind of non-behavior, that's under reasonable conditions, the behavior does not depend on x. Okay, so this is fixed. You can take any, basically that says in every site, you got a high-rise building with an equal chance. Okay. So here, so is what if that a kappa is not a superlinearly increase? If that's so, you are going to say this supreme is going to be infinity for the large lambda. That means it's highly unlikely you are going to see the high-rise building in, in a reasonable chance. So that's not the intermittency. Okay. Another case is you want to say that observe this intermittency image, but I don't want to wait for a very long time. I don't want to wait for 100 years to say what happened. So I want to say what happened for the fixed t. Then I'm going to consider this high moment asymptotics. Why? The reason I want to consider this is also by that Gardner-Innes theorem, you are going to get this kind of expression. Okay. This expression by the same ways shows that's the intermittency for the fixed t. Okay. Of course, there are some other ways to describe intermittencies. For example, we may consider the Quenched laws. For example, you may ask what will happen. This stochastic process behaves when the t goes to infinity. What will happen for this quantities goes to behave when r goes to infinity, particularly for this. Look, sometimes we just want to say how often we say that's high-rise buildings, how high those rise buildings in those large areas. This is the way we describe that. Okay, so that is the motivation why we study the large-scale large-scale asymptotics, because we wanted to know something about intermittency. Okay, let's get more mathematics. Most of the talks, actually in this talk, we are going to consider the case where that's the random potential is Gaussian noise. Typically, we are going to consider this noise is giving us a formal derivatives of some Gaussian field with stationary increment. Okay. We know that if you intuitively, if you take the derivative for a stationary increment Gaussian field, then this derivative must be stationary. So we are talking about, as a noise, we are talking about the stationary Gaussian field. If this Gaussian field is stationary, then its covariance, which is the way we decide the distribution, will be giving us a function of increment of the parameters. So that's why that is given like this form. One is covariance function for the time component, another is for the space component. And one of the assumptions we are going to assume from beginning to the end is the homogeneity for this covariance. So our process Gaussian field have some homogeneity given like this. So under this assumption, we can say that immediately that those gamma functions blows up and zero. Remember, so for the variance is a special case of covariance. That's a special case when t equal to s and x equal to y. So this phenomenon basically says that our Gaussian field we talk about have an infinite variance from at every point. Of course, then that basically says this Gaussian field is not point-wise defined because the singularity given here. That is giving us a generalized Gaussian field. Another thing I want to say is those alpha zero play a major role in formulating our theorems. Here, the alpha zero, giving us a measurement of the singularity of our covariance functions. So one of the very important case is the fractional Gaussian noise. Basically, that is giving us a formal derivative of the fractional Brownian sheet with the parameter, Hurst parameter given like this. In this case, we can have a homogeneity we talked about in the previous page with alpha zero, alpha is given in terms of those H values. And this is perhaps the most important class of the noise in this talk. Okay, any questions?
Okay.
All right. So mathematically, of course, the way we write in the, previously, the way we write the Parabolic Anderson model is just symbolic because because that's the field Gaussian noise is not point-wise defined. In order to mathematically define that's the to define that the equation, we have to define that in terms of this integral integration equations, where this stochastic integral can take different meanings. Then you may get a different setup for these equations. In this talk, we are going to consider the case where this integration is given in the sense of Ito Skorohod. Okay. So I think if I noticed that the name of this seminar is have something to do with the Malliavin. So if you want to find any link between this talk and the Malliavin, here perhaps it is. Then if you just iterate, so that's a linear integral equations, you are going to get at least in form of this kind of expansion called the Ito-Wiener expansions. And here, that's all the terms are orthogonals, means the covariance between those different terms is 0, okay? So if you, for this, if you take that second moment, immediately you get this kind of expression, at least in form. So naturally, this solvability problem, although this is not the main topic we give here, is given in terms of the summability of this series. Okay. To me, this is important. When Ito-Wiener chaos expansion can derive at least in form of expression of this, for the solutions. But I say this is just symbolic for most of the case because this moment will blow up, okay? But if you derive from here, start from here, and to do some computations, you are going to get rigorous moment representations. And we call this Feymann-Kac representation. And this is my starting point, because if you ask those asymptoticals related to the moments here, and that is a standard large deviation problems.
Here, can I have some question related to the previous slide? Can you show us this
Yes.
Feymann-Kac representation for solution? Yeah. So you said that one can prove that there exists solution for this equation. It was equation with Ito-Skorohod integral.
Yes.
And here you use expression like this. This is formal expression like this derivative was a real potential. Then it will be true. But let me ask you, is it related really to Ito-Skorohod integral or to Stratonovich integral? Can one check formally that this solution can be represented in this way? Or this is just formal expression?
This is a formal expression because this does not make sense. The link to that to Ito integral or to that Ito-Wiener chaos expansion is, I remember I learned, Andrew, I remember I learned this from you. So you told me that's how you write this kind of expression in terms of that's a chaos expansion to Hermite polynomial. I remember that's 10-some years ago in Hangzhou, you told me this trick.
Yes.
How we can do it.
Mm-hmm. But at those time, we do not know. At least I remember that the solution really exists for those problem. But nowadays people can do this. Yes.
Yes. Also,
Okay.
this thing does not make sense. But if you compute, so this thing does not make sense. In order to make sense, you can smoothize the quantity. Then you take a limit. Once you smoothize this quantity, take the moments, you are going to get something like this. And take limits. This part is real. But under all condition of solvability, this part is well defined.
Okay, thank you.
Okay, now I'm started. Now I feel that I got almost half of the time, so I always have to start with those the large scale asymptotics. So here is the result, one of the results, and so this result. In this result, we consider the case where the time is cornered, means this alpha 0 is less than 1. So in this case, we have both long-term asymptotics and high moment asymptotics. You can, okay, I'm going to tell you what the variation E in next page. But when you look at those two asymptoticals, you see obvious universality, means that if you change the order, okay, just switch between the T limit and M limit, you see those two things more or less take the same form. I call this universality. You are going to see a lot of universality in those results. Okay. Here, that's the E is a variation given in this form. And sometimes this E can be, evaluated into a specific numbers. This kind of variation form in literature sometimes we call Vardan function. It's because when the Vardan apply his large deviation scales to some physical models like a parallel, those are variations. Those are variations appear in his paper. Now I'm going to talk about the slightly different case where the noise is white in time, means this alpha 0 is 1. In that case, this time covariance is given in terms of direct functions. In that case, we noticed we have a simple form for this moment representation before you have double integrals. But since you take this delta functions, that's the fourth double integral into a single integral, like this. Then we are going to ask the same question: what happened when the t goes to infinity, and what happened when m goes to infinity? So here is the result. First, let's talk about when the t goes to infinity. The people may think this is an easy problem. Well, why? Because if you have this kind of expression and you ask the large T behavior for this kind of things, you can use the same group method. Okay. To write your limit in terms of variation. So that's exactly what we did here. But the problem is, so that is easy. But if you ask to write this variation explicitly into a function of m, that's hard. That's hard. Actually, this is analytical problems. Even that's an unsolved analytical problem so far, in most of the case. So I'm going to leave that to the next page to address what's happening to this L. Okay. For the high moment here, that's easy. So that's giving, just like before, And we also can give some kind of asymptotical universality. Take m goes to infinity, and you can have some asymptotical interpretation of this limit given here. So, like I said, that's an interesting problem is to find exactly dependence of on m for this limit. This is an unsolved problem, except the case where your noise also space-wide. Okay, so in that case, you have only one dimension model, and time and space are wide. In that case, we have following expression, and this gives a story about the limit. This result was studied by those Italian mathematicians. No, those are the physicists. And they give something slightly stronger than this, but later on we found that the result was wrong. And so I started to do this, and this is correct. Of course, then we may ask, what will happen when the time is wide and the space is arbitrary? This is my conjecture given here. And if this is true, you say that this will give a very different, not very different, but slightly different picture, you know, compared with the case where the noise is cornered in time. So you say that the difference is here and here. So there's no explanation why when you come to the white, you are going to have a slightly different expression. Another thing, there's some problems still not solved. That is when the time is rough. So here it is. So we have three different phases. The phase one is that the time is cornered. That is the case where the time component have a less singularity than the white case. Another phase two is that this alpha 0 is one, that's the whiting time. So we say that from our main theorems, when alpha 0 is greater than, well, is less than 1, you have a super linear increasing. When this alpha 0 is equal to 1, you have a linear increasing rate. Then you consider the rough case where the alpha 0 is greater than 1, you may naturally, guess that the increasing rate for the time intermittency will be sublinear. But that was not right. Actually, you get when you start to consider the rough case, then the model will keep a linear increasing rate. Although this problem is largely unsolved because we don't, first of all, we can only consider have the limit for the second moment. And secondly, even in this case, we only have a genetic number here without knowing anything about this number cannot be written in terms of any variation for that. So this is remain unknowns in the rough case. Now, what I'm talking about so by far is what we call earlier case, means you talk about the moment of the solutions. From now on, we are going to talk about the Quenched asymptotics, means you are going to consider the limit for that's the random for the stochastic process or field U. So one of the, well, I'm going to start with this space asymptotical problems. And the first, this type of result appeared 7 years ago, and that's what they got. So you can see from here, interpretation is this. If you think this as a, you know, U as a surface, okay, and you cover a big part of the surface, you ask what is the highest mountain I have been. This result more or less to tell you that with the increasing of your search areas, how high that's the highest mountain can be, okay? Then the natural question is, can you get a more precise result? So that's my result. And so in this result, I can write that precisely in terms of some constant. Like I said, in some situations, this constant, this variation can be solved in terms of specific constant. One of those cases is when the b equal to 1, and this noise is white in time and space. And in that case, that's the right-hand side can be evaluated in terms of numbers. That's it. And the reason I list this result specifically is because this link to the KBZ equation. Okay, here it is. Remember, that's the KBZ equation, and the relation between KBZ equation and the parabolic Anderson is given by this transform, and therefore, no, as a corollary, you get that's the limited result for the KBZ equation. Okay. I'm going to, normally, so this introductory talk, I should not give the proof, but here I give a simple argument for this result I just talked about to show that's the link between some of those earlier moments or asymptoticals and to the, you know, to those quenched result. So if you want to show that those the quenched result I just mentioned, those things, for example. And you know, that's for the strong limit. We know that so far, when you try to establish a strong limit, the only way out is the Borel-Cantali limit. So that's what we do. So you need to get these things, and then you can solve them, you prove the result. So the first thing is we wanted to say is the solution of Parabolic Anderson have some kind of continuity. Because you have a continuity, you can discretize this maximum problem to the maximization over some discrete point, okay? Then, so you work on the right-hand side, the upper bound you need is given by this. So then to give the bound, then you need to ask the question about this tail probabilities. The next page, I'm going to show this probability also become relevant when you come to the lower bound. So for the lower bound, if your QK, that's the index set, is the set where the point keeps some suitable distance, then you are talking about the maximum of a bunch of those random variables which are nearly independent. Let's assume that's independent. Then you are going to get this expression. So say that for the lower bound, you also make this probability, same probability relevant. That's this. Ask the question of this. And this thing become easy is because our high moment asymptoticals we talked about before actually provides the way to give that to decide that tail probabilities by the Gardner init theorem. That's the more or less the proof here. Okay. Then the next question is the quenched time asymptoticals. Before we ask when that's the x goes to infinity, roughly speaking. Now we ask, what if the time t goes to infinity? And you want, for example, some almost sure limit behaviors for the solutions. This, to some degree, is a very difficult problem. So I start with a special case where of the time independent, means this noise can have only space component. Okay. In that case, we may get a Feymann-Kac result. Okay, this time, everything is well defined. And basically, so this expectation is taken to the Brownian motion. So this remain stochastical because it's stochastical of the noise. Okay, so you ask this kind of what happened almost surely when the t goes to infinity. Actually, this problem was raised by early papers of Carmona and Molchanov. They basically have a conjecture like this. So my results actually found that actually results is slightly different. Before this, remember in their conjecture, this power is take a different numbers. So that's our result. And again, that this E is given in terms of variation we gave before.
But probably T should be absent in the right-hand side.
Sorry? T?
You have a limit in the left-hand side, but in right-hand side you have T also.
Yes, we have a D. So because our problem is D-dimensional. So there
No, what is T, not D, but
oh, T, sorry. Yeah, that's a mistake, sorry. Yeah. That's a mistake. Get rid of this thing equal to 1. Okay. Thanks. Right, so there's no T here. Of course, later on, we also give a result where the this noise is rough, means that's the edge, means that alpha is greater than 1. This results more or less the same type. That's just later on we just fight against the roughness. Okay. Quenched time asymptotics for the time-dependent case. So now this time we consider the same kind of problem where that's the noise is depends on T. Actually, this makes a huge difference. Most of the results we have seen in the literature, in this case, is given of this type. And remember, that's when you have a time-independent case, this part, you have a log part here, but you don't have a log part here now. There is some, that basically says that dependence on the time completely changes the dynamics of the system. I wish I have more time to explain this, but so I let it go. In most of the case, this C0 is not, have no information about this C0 except that's positive and finite. Only one case, the case where okay, here I forgot to type more things here. So this second result is a spatial result for the case of one dimension and time space-wide. I should say this, okay? So you have this result. I believe you still remember somewhere in my talk, you have said this 1/24. There's some relevance there. So only in that spatial case, you can get the C0 equal to this. So this actually become very difficult problem. I mean, first of all, in general case, to find this C0 is not easy job. The C0 largely remain unknown. You can make this problem is even harder to consider that the limit of the second order. By far, the most significant result was the result I listed here. So for this result, you see that this part actually, the term T/24 is relevant to this expectation we give here in that case. And so in this particular case, they get the weak law of convergence, where that the limit is given in terms of a Tracy-Weider law. That is most often appeared in the particle interacting particle system, or in that's the theory of the rundown matrix. So this effort, so those three peoples, some of them is working in the one working in the particle system, another rundown matrix, another is in the Parabolic Anderson. So those three combined their force together get this result. Of course, one of the question is, we wanted to say that in general case, can you get some result like this? Andre, if you still remember in G-Lin, this time we are discussing about those concentration inequality.
Yes, I remember this, yeah.
To know that is for this purpose. Okay, now I have 10 minutes. I add something more here. So because this, like I said, the name of this seminar is about the Malliavin calculus. I have to show more Malliavin in my talk. So this is my effort. So I add those parts yesterday. Before, although that's a Parabolic Anderson model have something to do with Malliavin, but once you establish the Feymann-Kac and you want to do large deviation, the Malliavin become less relevant to the problem. We have to confess. Then recently, I'm working in a wave equations. So here you see the difference. Instead of the derivative of the first order, you take a second derivative. That's totally changed the dynamics. Of course, there's something remain the same. For example, you still can interpret this, equation in terms of integral equations with in the sense of square hole. Okay. You still can write your solution in terms of Wiener chaos expansion. The solvability still can be checked by the convergence. So for the solvability, I don't think that will have a extra difficult if you move to this wave equations. But to me, that is bad because we don't have a Feymann-Kac in this case. It is proved in this case, you cannot have anything you call Feymann-Kac representation, okay? Now, this gives a challenge. So the large deviation scale have to directly apply to the Ito-Wiener chaos expansion. And that's the challenge. That's why I put the title here, says this word, that's a Varda, we know that's the leader in large deviation areas meet the Malliavin. So that's interesting to me because I wanted to see how that's the large deviation can reach to the what we call complicated system like this. Here is some result we just obtained last week. So make life easier to begin with, we take that the noise is a noise of time independent noise. Then we will get some results like this. And where that's E is more or less the same as before, that's a variation of the same type. So that's also represent the Varda. So that's why I call this Varda meets Malliavin. So this is so basically I'm happy that we may develop a way to applying applying the large deviation scales to Ito-Wiener chaos expansion. We know that the Ito-Wiener chaos expansion is far beyond the model we talk about here. A lot of random field or it can be written in terms of Ito-Wiener chaos expansions. I hope that we are going to develop a systematical methods to deal with that chaos expansion and to establish. So the idealistic goal is this. If you give me a specific Ito-Wiener chaos expansion, then I can tell you something about the large deviation about the model. That's our final goals. Thank you very much. Here is the list of the references. Thank you.
Thank you very much. It was a very interesting and very intriguing talk. Does anybody have questions, comments, please?
May I ask a question?
Yes.
Could you please once again explain what did you mean by saying that there is no Feymann-Kac formula for wave type of equations?
Okay.
What exactly did you mean?
Okay, to answer this question, let's go back to the Feymann-Kac.
Yes, yes.
Okay, here. So those are what I mean by the Feymann-Kac representation. Oh, let me read it earlier. Okay, so the general case. Here it is. This and this.
So in terms of, roughly speaking, in terms of diffusion and our potential.
Sorry?
So this is a Feymann-Kac formula in terms of diffusion and our potential W dot. Yes? So what was your statement for the wave type equation?
Okay, so this is for the Parabolic Anderson.
Yes, yes, yes.
So this basically says you treat this W at least formally as a deterministic function. Okay, so you get this.
Yes.
So you know that the Feymann-Kac basically says when you start with Parabolic Anderson models, this model is defined to have nothing to do with Brownian motions, but you can, express this as an exponential moment in terms of Brownian motion. The Brownian motion is getting the picture because of this things.
Okay.
Also, sometimes this is too singular, but morally, this is still live in our minds. But if you want the mathematical rigorous representation, this is. So then at early times, when the people started with wave equation, even wave equation where the potential is deterministic or nice, deterministic potential. So that means singularity will not play any roles.
So just a PDE, wave equation with potential, yes?
Right, deterministic PDE.
Yes.
Then there are results, early results. I think that is 2008 or some, you know.
So there is a Feymann-Kac representation, but not only diffusion involved, but also some Poisson processes or whatever. Yeah?
Okay. So they were talking about started with an even simpler model, that is a potential deterministic. Then they show us that you cannot find any Markov process. This is process on emotion who make something like this and something like this. They show us this. So that's what I mean. There's no such explanation, expressions.
Okay, my question is motivated by the fact that I have seen a paper, and probably we are talking about the same paper, but I can be wrong. But the year 2008 seems to be the same year.
Right.
And there was a kind of Feymann-Kac representation for wave equation, just PDE. And this Feymann-Kac very
there's, I think sometimes the people, when they refer to Feymann-Kac, they mean a different thing. So if I remember correctly, in that paper, they give some kind of something looks like what later on we call Ito-Wiener chaos expansion, right?
Well, I don't remember. I have to look at the paper, but I was
another thing I want to point out. I want to point out, so thank you to remind me this one. So they are talking about also represent that's the result in that Ito-Wiener chaos expansion into some kernel of stochastic process, but that process should not be Markovian. The reason that's
this could be this. This could be
because in the structure of that process, the future. So the history was decided by the futures. You remember that? So of course that's destroy any Markovian properties. So let's assume I don't know this part. Okay, so let's assume you may get this kind of representation where this Brown motion is replaced by some process which is not Markovian. Even you can that will not help me very much. So why I cannot do much with this representation.
Okay, well, thanks for your answer.
Okay, thank you.
Okay. Some other questions, please. Xia, I have a following question relatively to your last result about large deviation for this wave equation. You said that you discussed the large deviations for
just hold on for a moment. Okay, let me just turn the page. Okay.
You said that you are trying to find the general method for find large deviations for random field via chaotic representation. Let me ask you, in this particular case, can you say, for example, that the first term or some few first terms from the chaotic expansion gives you main impact into the asymptotic of the large deviation?
No. That's actually is I can show that's not the case. Certainly, you have to have the whole terms. Particularly, let's say if you consider that's the case. Let's say if you want to consider this type of result, you have to so among those expansions, there of course have one or two terms which play the dominant contributions to this problem, this kind of problems. That term with n which depends on t in some way.
Oh, I see.
Yes.
I see. Interesting. Also, let me ask you. This is related question, but to the previous slide, you mentioned it when you explained the application of the Borel-Cantelli lemma.
Yes.
You mentioned that let's suppose that the random field UTX has independent values.
Time independent. What do you mean by that?
No. I just consider the proof of this asymptotic of large precise asymptotic of behavior of logarithm of UTX for parabolic case, and you said that when applying Borel-Cantelli lemma,
Yes.
you substitute in the suprema, you substitute the suprema on the big box, just suprema on the some points.
Yes. Yes.
Yeah, and say suppose that the value of the field is are independent in these points. Yeah.
Yes, we in our mind we are thinking about those independent points. Yes, but that's not really independent.
Yes. But I just ask, can you say something that this random field U have some mixing properties with respect to the space variable or not?
Right. That's exactly what I mean by nearly independent.
So you can estimate this mixing coefficient and so on.
Yes. Of course, this is a little bit technical. So there's a two. So proof of this result. There's a two sides. One side is an upper bound. Another is lower bound. So for those two different parts, this QK may be different. For the upper bound, you want to make this really equal to that. So the points have to be close to each other. So you don't use the independence. Actually, they're very much independent to each other. Only for the lower, in order to make independence, then you make those, points keep distance from each other to have independence.
I see. Okay, thank you very much.
Thank you.
Okay, maybe some other comments, please. Okay, if there are no any other comments, I have to thank Xia again for very interesting talk. And I hope that this is only introduction, and the next semester things will go in the good way, and we will see you in Kyiv. And
that's what I wish.
And you will make some series of talk on these topics.
Okay.
Also, I have to say that this is the last seminar this semester. Next semester we will start from September. So everybody who want to make representation have to contact secretary of the seminar near 15th of August. We will send some emails to recall this to participants.
Will you continue in Zoom or already in Kyiv only?
Yes, I suppose that we will mix our way to organize seminars. So we will, of course, continue Zoom presentation, but maybe if somebody will visit us, like here, then we will use ordinary room, but we will have a camera and you will have a possibility to
participate.
Exactly.
Okay, thank you very much. Perfect.
Okay, so thanks everybody.
Have a nice summer, everybody.
Have a nice summer. Goodbye.
Bye.
Goodbye. Thank you.
Okay.
Goodbye.
Bye bye.
Bye.